In this section, we are talking about comparing two different population means. So
Describe,
the
again,
objectives
the shape,
for this
center,
section
spread
of the sampling distribution of the difference of two sample means. Determine whether conditions are met for using inference about the difference of two means. Construct and interpret a confidence interval to compare two means. Perform a significance test to compare two means. And determine when it's appropriate to use two sample T procedures versus paired T procedures. And that'll actually be next week, or the next lesson. So what if we want to compare the mean of some quantitative variable for the individuals in population 1 and population 2? Our parameters of interest are the population means, mu sub 1 and mu sub 2. The best approach to take is to separate random variate samples from each population and to compare the sample means. Suppose we want to compare the average effectiveness of two treatments in a completely randomized experiment. We use the mean response in the two groups to make the comparison. So again, just like before in our last section, our population treatment, we would have either a population or a treatment, and we would have two different ones. We have two parameters, two statistics, and two different sample sizes. Notice again the parameter mu for population and statistics x bar for our statistics. Population, sample. To explore the sampling distribution of the difference between two means, let's start with two normally distributed populations having known means and standard deviations. Based on information from the United States National Health and Nutrition Examination Survey, the heights of 10-year-old girls follows a normal distribution, and the heights of 10-year-old boys also follow a normal distribution. Notice that for the girls, it's 56.4 inches with a standard deviation of 2.7. Suppose we take an independent, simple random sample of 12 girls and 8 boys of this age and measure their heights. What can we say about the differences in their means and the average heights of the samples of boys and girls and the sample of boys? They're using F and M for female and male. Fathom software, we generated a simple random sample for 12 girls, right here, and a separate simple random sample of 8 boys, and calculated the sample mean heights. The differences in the sample's means was then calculated and plotted. We repeated this process 1,000 times, and the results are below. So here's the girls. Notice it's a pretty normal shape. Here's the boys. Again, also normal, and so is the differences. The mean for the girls is right at 56.4, which was the mean of the population. The mean for the boys was 55.7, which was the mean of the population. And look at the mean of the differences. 56.4 minus 55.7, 0.67 inches. So we are subtracting them. The standard deviation, or the spread, 0.8 and 1.35, we cannot add them or subtract them like before, so we have to figure out another way to find both the spread. X bar sub 1 and X bar sub 2 are random variables. The statistics, the difference of those sample means, is the difference of these two random variables. In Chapter 6, we learned that for any two independent random variables, X and Y, the mean is you subtract the population means, and the standard deviation, you actually have to use variance and add the variance together. So, shape, when the population distributions are normal, the sampling distribution of the differences will also be approximately normal. In other cases, the sampling distribution will be approximately normal if the sample sizes are large enough, just like before, if the sample size are bigger than 30. The center is the mean of the sampling distribution. Take the population mean minus the population mean. And to find the standard deviation of the sampling distribution, it's the square root of the population variance over the sample size plus the population variance over the sample size, as long as each sample is no more than 10% of its population, the 10% condition. So here again, we have a normal curve. We have one standard deviation away. All the values of the differences would be along the x-axis, and this right here, the mean of the populations, is going to be your center. When data come from two random sample or two groups in a randomized experiment, the test statistic x bar sub 1 minus x bar sub 2 is our best guess for the value of the population. When the 10% condition is met, the standard deviation of the sampling distribution can be found using this formula. And if the normal condition is met, we standardize the observed difference to obtain a t test statistic that tells us how far the observed difference is from its mean and standard deviation units. Remember, back in the last chapters when we were working with population mean, we used a t-test. Since we don't know the values of the parameters sigma sub 1 and sigma sub 2, we replace them in the standard deviation formula with the sample standard deviations. The result is the standard error of the test statistic. So then t, remember, is the sample minus the population divided by the standard deviation, in this case the standard error. The two sample t statistic has approximately a t distribution. We can use technology to determine degrees of freedom, or we can use a conservative approach using the smaller of n-1 and n-1 for the two populations to find the degrees of freedom. So here again is a summary of the conditions that need to be met. Has to be random, has to follow the 10% rule, and it has to be a normal or a large sample. So it either needs to be greater than or equal to 30 for both sample sizes, or when you graph the samples, it has to have a pretty decent normal shape. There can't be any strong skewness or outliers. When the conditions are met, an approximate C% confidence interval for the difference in the population means is going to be your test statistic plus or minus our t times our standard error. T is the critical value with C% of its area between negative t and positive t for the t distribution with degrees from freedom either from technology or the smaller of n sub 1 minus 1 or n sub 2 minus 1.